Hello there, and I want to do some oxidation assignment examples for you guys. And our first one is a oxidation reaction of copper, which will eventually lead to the patining of copper. In this case, this is the reddish pink form that it forms. So in order to do this, we're going to look at our reactants first. So we're going to start off with our copper reactant. And there's no other elements in this. It is a atom that is in its elemental form. And so we can look at our chart here and we'll follow rule number 1, where our oxidation number is going to be equal to 0. And so we can just put a line down and put a 0 to note that its oxidation number is 0. Then we're going to look at O2. All right, oxygen. This is also in its elemental form, as denoted by rule 1. And so its oxidation number will be 0 as well. So we'll put 0 down for its oxidation number. Then we go over to the product, Cu2O, copper oxide. And for this one, we have multiple elements within this compound. So our first two rules will not work because we have multiple elements. So we're going to have to go with number 3, which essentially just means that the oxidation numbers of all the atoms need to add up to the charge. In this case, there's nothing written down for the charge, so the charge is assumed to be neutral or 0. Then we'll need to follow this table here and determine what oxidation numbers we can determine, and then solve for the rest. So looking at this Cu2O, we can look at our first rule and decide if we have anything in group 1A. So lithium and down on the periodic table. Since we do not, we're going to move on to the next one. So we look for anything in group 2A, or the second column. And we don't have anything there. Then we look for hydrogen. There are no hydrogens. Then we look for fluorine. We don't have any fluorines. And then we look for oxygen. And oxygen we actually do have. And so in most cases, oxygen is going to have a -2 charge. If you know that your oxygen is bonding with fluorine or another oxygen, then it won't be a -2, but many times it is going to be -2. So we're going to put -2 up here. And then we look at our last one. Do we have anything in group 7A, or the halogens? And we don't have any of these species in this compound. So now we're left with copper. We don't know what copper is. So in order to solve for copper, we'll need to set up an equation to solve for the oxidation number. So we're going to take the subscript 2, meaning that we have 2 coppers, and we're going to say 2 times the oxidation number of copper, which we don't know, so we're going to just put it in a variable. In this case, I'm going to put x. And that is going to be added to the sum of all the other oxidation numbers. In this case, we only have oxygen. Since there's nothing written down here, we have 1 oxygen, and the oxidation number is -2. And so we're going to say we have 1 oxygen. We're going to multiply that by oxidation number of it, which is -2. And then all that needs to be equal to our charge. And our charge, as stated earlier, is nothing written down there. So it's assumed to be neutral or 0. And so now we can go ahead and solve this algebraic equation. We'll simplify it down. We'll say 2x plus our -2 is equal to 0. 2x minus 2 is equal to 0. Then we can bring that 2 over, add 2 to both sides. So we'll have 2x is equal to 2. And then to isolate the x, we'll divide both sides by 2. We'll get x is equal to 1 or positive 1. And so on average, each of the copper atoms are going to have an oxidation number of positive 1. So that's what we write down. Alright, and so now we're going to move on to another example. And we're going to look at dicalcium phosphate. This is often used as a polishing agent in toothpaste and is sometimes used as a food additive. So we can go down our rules here and we can say, alright, well, do we have anything in group 1? Alright. And we do have hydrogen, but hydrogen has its own set of rules, so we're going to leave that one alone for now. Then we look and see if we have anything in group 2. Alright. In this case, we do. We have calcium. So we can go ahead and mark down calcium to be a positive 2 oxidation number. And then we do have a hydrogen. Alright. And in this case, we say that hydrogen is going to either be a +1 if it's bonded with a nonmetal, or a -1 if it's bonded with a metal or boron. Now in this case, we have both metal, calcium, and a nonmetal, such as phosphorus and oxygen, or phosphate. So we're going to have to hold off on this one because we don't know. It could be a +1 or a -1. Then we're going to look at fluorine. Alright, we don't have any fluorine, so we're going to move on to the next one. Then we look at oxygens. Now we do have some oxygens. Now, one of the tricks to solving this thing very easily is to recognize that we have this PO4. Alright? PO4 is a very common polyatomic ion. It's a phosphate ion. And so we can go ahead and break this down. We can go ahead and say that we have oxygens having a oxidation number of -2. But if we go ahead and pull this aside, we can say we have PO4 3-. That's the charge of the phosphate ion. And we can go ahead and solve for it. Now, we could do this, or the other way is to go ahead and say, well, our hydrogen is probably attaching to this phosphate and give it a +1 oxidation number, which would be legitimate. But either way, you'll end up getting the same answer. So I tend to like to look at the polyatomic ions as they normally stay fairly consistent. So let's go ahead and put our -2 on our oxygen. Then all we need to do is solve for the phosphorus. So for phosphorus, we have 1 phosphorus. We're going to put in our variable of x because we don't know what the oxidation number is. Then we're going to add that to that of the oxygens. So we have 4 oxygens. Multiply that by the oxidation number of -2. And then this is going to be equal to our charge. Alright, our charge of our polyatomic ion is -3. And so now we can solve for this algebraic equation. So we'll have 1 times x giving us x. We'll have 4 times -2 giving us -8. That needs to be equal to -3. We'll have x minus 8 is equal to -3. And then we can bring 8 over by adding 8 to both sides. And we'll say x is equal to 5, or +5. And so if you know what your oxidation numbers are for your polyatomic ions, that holds true when you combine them with other species. So whenever you see this PO4, you'll know that the phosphorus is going to be a +5, and the oxygens are going to be a -2. And then you can also realize that the rest of the species attached to it, their oxidation numbers need to add up to a positive 3 if it's in fact a neutral compound. But that is one way to solve it. The other way to solve it would have been to assume that the hydrogen would be positive 1 and add up the sum total of all these oxidation numbers, set it equal to 0, and then you'd also come up with a positive 5 as well. Alright, let's do another example. And this time we're going to look at another reaction, the formation of rust. So similar to the first one we did. In this case, we have iron combining with oxygen to form iron oxide. And so we can look at our first rule here, and if we're looking at the iron on the reactant side, we'll see that it is in fact in its elemental form. So it's going to be a oxidation number of 0. On the reactant side, we have O2, and it is also going to be in its elemental form, giving it an oxidation number of 0. Alright, then we finally get over to the reactant side. Now we have our iron oxide here, and one thing to kind of keep in mind is you don't need to worry about these coefficients here. That doesn't really affect the oxidation numbers of the molecule. And so we can quickly go through our list again. For Fe2O3, we don't have anything in the first column of the periodic table, so we can keep moving on. We don't have anything in the second column of the periodic table. We don't have any hydrogens. We don't have any fluorines because iron, capital F, lowercase e, is not fluorine. It is iron. And then we finally get to oxygen, and we do have oxygens in this case. So oxygen is normally -2. We don't have any fluorines. It's not a peroxide, so oxygen is going to have a -2 oxidation number. Then we need to solve for iron. All right, we don't have anything in our halogens, so we're going to solve for iron. And so in this case, we can say that we have 2 irons, and so I'm going to say 2 times our unknown, X, oxidation number for iron, plus 3 of our oxygens at an oxidation number of -2. So 3 times -2. And all that's going to be equal to the charge, which in this case there's nothing written down, so it's assumed to be 0 or neutral. And then we can solve for X. So we'll say 2x plus 3 times -2, giving us -6, is equal to 0. We'll have 2x minus 6 is equal to 0. We can bring the 6 over by adding 6 to both sides. So 2x is equal to 6. And then isolate x by dividing both sides by 2. X is equal to +3. So the iron in iron oxide has a +3 oxidation number. Alright, let's finish up with one more example. Okay, we're going to look at potassium dichromate. So this is sometimes used to stain certain woods, like mahogany, to give a darker coloring, a dark brown coloring. And this can be similar to our second example we did. And this time I'm going to go ahead and say, let's go ahead and isolate this polyatomic ion. We'll go through and we'll find that potassium is in group 1, so we know it's going to have a +1 But whenever you see a polyatomic ion, I recommend just go ahead and pulling them out. If you look on your useful equations packet, there's a list of polyatomic ions. You don't have to memorize them. I recommend you just look through them so you can maybe recognize them. So if we pull out this potassium dichromate, if we pull out the dichromate ion, we'll have Cr2O7 2 minus. So that's a -2 charge. And then we're solving this. We go through, we don't have anything in the group 1, part of first row. We don't have anything in the second column. We don't have any hydrogens, we don't have any fluorines, and then we have oxygens. Now oxygen is normally going to be -2. How many other oxygens are combining with each other? It's not peroxide, and it's not bonding with any fluorines. And then we don't have any other halogens. Chromate is a transition metal, so we're going to have to solve for it with a variable. And so we're going to say we have 2 chromates. We don't know what the oxidation number is, so we're going to set that to x. So 2 times x, our oxidation number for chromate. We're going to add that to our 7 oxygens with the oxidation number of -2. So 7 oxygens. The oxidation number of -2 is going to be equal to our charge. Our charge in this case for the polyatomic ion is 2 minus, or -2. And so just kind of as a reference, what we're going to do is I'm going to go ahead and put some shapes on here so you can see where everything's coming from. So we have our 2 chromates. We have our 7 oxygens. We have a oxidation number of oxygen to be -2. And then finally we have our charge with this little shape. Alright, so that's where everything's coming from. And again, all we need to do is solve the algebraic equation. And so we'll say we have 2x plus 7 times -2, giving us a -14, is equal to -2. We'll say 2x minus 14 is equal to -2. Add 14 to both sides, we'll have 2x is equal to 12. And then to isolate the x, we'll divide both sides by 2, and we'll have x is equal to 6. And so for our chromate, it's going to be a positive 6. And so now we can start solving it for our actual compound of potassium dichromate. So the oxygen is going to be -2. Our chromiums are going to be positive 6. And then we can solve for potassium. We know that both potassiums need to add up to a charge, our oxidation number that's equal to the charge of a positive 2 to make our chromate 2 minus balanced. Or we can simply just say it is part of the group 1 elements, and so it's going to be a positive 1. Alright, well hopefully these examples helped you out, and I look forward to seeing you in the next video.